Okay, in the Greek era, we have really big kind of big bang in math, and the outcome, one of the outcome, is the Euclid's Elements. It's a book. Actually, it's, consists of several books, but he did really amazing job to arrange all these known facts. Okay, many portion is not by done Euclid, but he just collect all these informations and arrange them in certain way, and that is really revolution of the whole math. So he tried to arrange them starting with the axioms or the postulates we call, and which is not required any proof. We just accept as a true statement because he realized whenever we try to certain fact, then we need to some other help, right? It must be using some other known fact. Then we need to prove that one. Then we also need another previous theorems or statements to prove these new ones, right? So it's just never ending, right? It's backward. So he believed, like, we think he realized that no matter what, we have to start with certain very important and core statements without any proof, and let's just accept it. And using these so-called axioms, we could prove all the other statements if it's true. And in that point of view, he was really amazing, but there are some kind of missing spots there. For example, like how about terminologies, some words? Okay? If we need some other theorems to prove these new theorems and just going backward forever, then same thing happens. When whatever the word we are using, we need definition of it. The meaning of defining a terminology means it requires many other new terminologies for that. Then we need definitions of all these terminologies. Then we need other words beforehand, right? So it's also going backward. But he didn't mention about that. So kind of natural way, for example, he defined the point as something does not have any parts. Then as you can see here, what is the meaning of part? And what is the meaning of does not have part, right? Something doesn't have any part. So if you really kind of look at that definition really critically, then yeah, it caused all the trouble. But he didn't realize that one. Maybe he thought this is kind of easy and natural. Yeah, of course, but okay, in our point of view, it's not that much clear. Okay, so anyway, what he did is really amazing. So he just wrote in this geometric true statements in certain order, and he accept these postulates n list. Okay? So that is amazing. And one of the postulate number 5, is known as Euclid's parallel postulate. It's really something cause all the, not trouble, but kind of interest of all the people. And later, recently, it turns out that we could play a god. Okay? So like, okay, it looks like meaning of parallel line is two lines never intersect. Okay, so if we move our position, we can check those parallel lines never intersect, right? Whenever we choose our positions like that. But we cannot go all the way to the infinity, right? That means at some time we have to just look at this parallel line at certain position. So just imagine we are sitting in between the two train tracks. Then these two train tracks looks like intersect at the infinite point, right? And both direction, right? Like that. So what we are seeing for the whole universe and whatever, who knows, maybe that is true, right? Not this way, because we cannot go there, right? Then instead of his fifth postulate, like any two parallel lines never intersect, how about we assuming they intersect? Or not even the statement says it's unique, right? But how about the parallel lines are not unique? Okay? It might be more than one, right? Passing same points, but still all these lines are parallel to this one, which means what? They never intersect. Okay? And it turns out that instead of Euclid's number 5 postulate, if you replace that one with any of these, like no, all the lines intersect, or there should be more than one parallel lines like that. Doesn't matter which one we replace that for this postulate 5. That system, that geometry is still true within its own universe. Okay, so we don't have time to discuss about this whole thing. It's going to be covered in modern geometry one course, but that is the big portion of it. And because of the lack of those missing spots in there, people try to make new systems, right, to fill in all these stuffs. So there's Hilbert and all the other people who try to make their own postulate systems. But it turns out that in around 1950, 1960, in the United States, there is a kind of reform movement in education and especially math. So this is the outcome of that movement. So we make our own, like a school mathematics for geometry or something like that. That's the one, that's the abbreviation of it. But this SMSG postulate system is like a new postulate system. And nowadays, any textbook, especially for middle school, high school textbooks, is based on this system in United States. Not other country, but this is just for. And the big difference between this postulate system compared to the Euclid postulate system is it accepts some measurements, some new stuffs. And the big difference between any other postulate system, including Euclid system and this SMSG postulate system is, for example, in Hilbert's postulate system, it really tried to get rigorous postulate system, which means it turns out that it's very difficult to prove the very simplest statement because there is no big tools developed yet in that system. So it requires a lot of work to just to prove very simple ones. And that is not good for in pedagogical point of view. We want to teach our younger students, right? And if it's trivial, then we don't want to spend time to explaining and to prove this rigorous the simple ones, right? So in that pedagogical point of view, this one is much better. So let's just kind of cut down all this mathematical rigorous, or I don't mean it's really kind of sacrifice that much, but it kind of sacrifice the completeness and independency of the postulate systems, right? It just, there are some redundancy in there, but because of that, the proofs are much easier. Okay, so what you have learned in high school and middle school and even college, some portion, actually it is written based on this SMSG postulates. Okay, so let's look at that SMSG postulate system. Compared to the Euclidean elements, we accept these three undefined terms: point, line, plane. Okay, then what is point? In Euclidean postulate system, it was what? Something does not have any part, right? It has only position, right? Right? You heard that one a lot. But in this system, we don't know what point means. What is the meaning of line? We don't know. No idea. So instead of point, you use like a fab or whatever. It's still okay because we don't care what real the meanings of those words. Then how we handle this geometry? Now, listen carefully. Whenever we have postulate system, there is kind of corresponding models are possible. So for the same postulate system, we could make different models, right? It doesn't matter. So in geometry, especially in plane geometry, no matter whether it's Euclidean elements, Euclidean postulate system or this SMSG postulate system, we will have at least one model for that. And that is what? This one and that, right? So let me ask you one question. I'm going to draw three different objects, right? Like that. Now, which one is a point? Number one, number two, number three. Maybe number one, number two, number three, or all of them, or none of them, right? The answer is none of them. If we follow the Euclid's definition, all of this has its part, right? No matter how small you just draw it, when you magnify it, it has a part, right? So it's not a point, according to that definition, right? So technically, it's impossible to sketch or draw a point, right? And how about line? No matter how you really accurately draw a line, is it really a line? It should be straight, right? And no thickness, right? It has a big thickness, right? So it's not a line. Okay? So because of this, what we have so far about geometry, like, oh, this is a triangle, that point, I mean, this line is perpendicular to that line. These are all lies. Okay? Surprise, right? What you have done, what you have learned is kind of lie, big lie. Okay? The systematic lie. These are a model of these postulate systems. So, point, we have an idea, but I could make some kind of model for that. Some people might do it different way, okay? And you don't care because there might be many different models are possible, but my model is what? Yeah, let me just give accepting this one as a point. So if you can make a bigger, smaller, okay, and even circle, you know what? It's known that there is no perfect circle in the world. You cannot make it. Okay? It always, there's some kind of dent in there. Okay? So it's a line. Yeah, it's a model of a line. Okay? So for any given two distinct points, there is a unique line passing through. We just accept it as a postulate. And this is a model for that. So words should be enough, like you can see here. But if you can sketch it using this model, it's much, much easier to understand what it claims, right? But the real meaning of point line do not exist. You can change that once whenever you give any concept there, okay? Any meanings on there. And without it, this is nice geometric model for that. So please keep that on your mind. Then these are about 20 something postulates in this system. And one big thing here, one big difference compared to the other postulate system is it's accepting the measurement. Measurement for line segment, measurement for the angle, right? And measurement for the area and volume even. So that's totally new things. And up to postulate number 15, 14, 15 is, no, 15, right? Because 16 is parallel postulate, right? So if you have any theorem use only up to number 15 postulates, we call that neutral geometry, which means we are going to talk about Euclidean and non-Euclidean geometry. So there is a big difference those two. But up to this, if any theorem use up to this much postulates and can be proved, then that theorem is true for no matter whether it's Euclidean geometry or non-Euclidean geometry. But starting from number 16, if you need any of these uh, postulates in your proof, then that theorem must be only true in Euclidean geometry. Of course, some of them are still true for both, but yeah, you can think that way. So it's not geometry course, so we're not going to cover this entire one, but please read and please be ready. And none of these middle school, high school geometry books saying they are based on SMSG postulate whatsoever, okay? But please keep this one for your record, and it's going to be very handy to see how they actually wrote that textbook. Okay, so let's just try to kind of prove some theorems here. And once again, there are many things which I want to talk about, like what is proof and how to show that proof and like that. But please look at here. The proofs consist of three parts. The first one is hypothesis, right? The condition part. And second part is the body. So it's a series of statements. And the last one is the conclusion. Okay? So restate of the given statement, right? But many cases we skip this, right? Because after showing this list of stuffs, we know okay, the entire statement is kind of stretching of this theorem. Okay? But most likely, we need three parts of it. In the many cases, people skip this hypothesis because it's already given in the statement. So for that case, and everybody understand that, yes, it can be also skipped, right? But for when you teach your students, please empathize to restate the given hypothesis because in math, everything depends on what is the given condition, right? So if you change the small portion of the condition, the whole arguments might be different. Okay? So checking what is the given condition is the key part of doing math. So we want to train our students think like that way, right? So for any proof, we have to start with stating what is the given condition, what is the hypothesis. So one of the good example for that is, what is 1 plus 1? If someone asks you that. Or even not using numbers, right? So if someone just asks me, yeah, what is 1 plus 1, right? Then what is going to be your answer? If you say 2, you're too naive. Okay? If you're saying, oh, maybe 2 plus minus alpha, then you might go to physics. Okay? Your major should be that way. Okay? Because we always have some errors in measuring or something like that. But if you are doing math in NIST or taking math courses, then your answer should be not like this, but like, okay, you just ask back to that person, what number you want as the answer. I can make it for you. Because you are playing God. Okay? So look at here, 1 plus 1. Yes, of course, we are so getting used to using that, right? So the answer is 2. But when that person asks you, what is 1 plus 1? That person didn't give you what is the meaning of 1, what is the meaning of plus. That person didn't give you the hypothesis, the condition. So if I adding my own condition in here, then the number could be all different numbers, right? The answer, right? So like this, the meaning of 1, 2, 3 is just number of water drops. And plus means just put those water drops together. So we don't care the size or volume of water drops. Just the numbers means how many water drops. Okay? And plus means put these water drops together. Now, what is 1 plus 1? You just put these water drops together, then you're going to have 1 water drop. So the answer should be what? 1. I can make 1 plus 1 equals 1000. How? I just define the meaning of plus to A times 1000 plus B. And according to that, 1 plus 1 is what? 1 times 1000 plus 1, which is 1001. That's what I'm saying. Your answer should be what? Oh, what number you want? I can make it for you. By what? Putting that condition. So meaning is, you have to ask back, right? Okay, what is the meaning of 1 and what is the meaning of plus when you ask me that question? Then you can answer it back there. Right? So when you're doing math, you just become picky, right? And why all your math teachers are so picky and okay, right? You understand? We are just trained think like that. Anyway, so let's just talk about sidetrack too much. But there are many interesting stuffs actually here. So hopefully we just work together later in other courses. But let's look at here. Let's just prove supplements of same angles are congruent. Meaning of supplement is what? Two angles are supplement means when you're adding these two angles together, it becomes 180 degrees, right? So let's just prove that. Let's say angle ABC is an angle. Okay, so let's say ABC. Okay. It's a given angle. That is for same angle. And supplement of it. So CBD and CBE, we are talking about two different angles, and we are claiming they are supplement of the angle AB. It should be C there. So let me just sketch like this, and that is D. So CBD is a supplement of this angle, which means what? It becomes 180. So this is a straight line, right? And let's assume CBE. So there is another one. CBE is also a supplement of that. So it's like this, right? Then ABD or ABE, both of them must be 180 degrees, right? And this one is for complement, right? So let's just forget that part. Then how can you get that cases if we have some non-zero angles between those two things, right? No way, right? Which means what? This D and E must be on the same line, right? On that straight line from there, okay? A, B, D and E must be around there. Okay? So which means what? Whenever you claim the angle is supplement of given angle, then those angle must be same angle, right? There's no other way. So same means is a congruent each other, right? So that's the entire proof here. Then vertical angles are congruent. Vertical angle means if two lines intersect each other, we call they are vertical angles. Of course, if you want, you can say these two angles are vertical angles each other. Doesn't matter which one you choose. Then because of the previous theorem, let's say A, P, B and C, P, D are intersecting at point P. Yes, right? Then APC, this angle, and DPB, that angles are supplement of the same angle APD, right? Because when you add APD and APC is 180, and APD plus DPB is also 180 degrees. And by the previous theorem, those two angles are congruent because they are supplement to the same angle, right? So this one shows those two. Any vertical angles are congruent each other. And in middle school, high school geometry course, they use this T proof, right? But it's not kind of new things. It's just the shape of these stuff. Good thing about that one is it's always asking, giving the reasons for that, why we can say that. Okay? So it's very important. So please just follow this one by yourself. It's going to be easy enough. And the next one is non-Euclidean geometry. People will say this one a lot. And actually there are two different types of non-Euclidean geometry. One of them is hyperbolic, the other one is elliptic. So the difference between those is like this. In Euclidean geometry, we call for any given line and a point, there is unique, only one, right? Line passing that point and parallel to the given line. This non-Euclidean geometry is separated into two parts. One of them is hyperbolic, the other one is elliptic. In hyperbolic, for any given line and a point, there are more than one lines passing that point and they are parallel to the given line. For elliptic non-Euclidean geometry, for any given line and the point, there is no parallel line exists. So no matter how you sketch the line, it must always intersect with the given line eventually. Okay? So no parallel lines. There is more than one parallel lines and unique parallel lines, right? That's the difference over there. Okay, so please just read those part, and these are the kind of model. Once again, what is such case like that, right? So this is a model for elliptic case, and hyperbolic case. It's Poincare disk model, but okay, it's not what we are talking about. So if you have time, we are going to cover later. But please remember this as a representative of those geometries. In Euclidean geometry, the angle sum of triangles is 180, right? Sum of the three interior angles is 180. For those non-Euclidean geometry case, one of them, hyperbolic, has less than 180, and elliptic case has greater than 180 case. So Euclidean geometry, yes, some of those are 180, right? But elliptic case, why is 180? Just imagine that elliptic geometry case, the universe or space looks like surface of a sphere. Just imagine that. And we draw this triangle on the surface of this sphere. Then when you measure those angles each, then it's one greater than 180. The worst scenario is, let's say this is the equator, okay? The big circle on the equator. And those lines are to the North Pole. Then definitely this angle is 90 degree, right? And for other points, we also get the 90. But if these two points are different ones, then we still have some angle there, right? So when you add these three angles together, definitely it's greater than 180 degrees, right? So once again, this is not the case. This is just a model, nice model to explaining what really happens in this elliptic geometry. Then how about hyperbolic geometry? That's the inside the disk case, right? So just imagine you are standing here, you never moves, and just look at whole universe. Then these are infinite points, right? All the directions. So if you just look at the same line segment very close to you, like close to center, or close to that far away from your position, then it looks like what? The one close to you is this much big enough, but for the same line segment, it looks like much smaller if it's far away from your position, right? But actually they are congruent, right? So in this format, whenever you sketch a line, then line looks like this, right? Okay, so there is something more, but just assuming that way. So it's a kind of an arc of a circle, which is orthogonal to this one. But so in that way, if you sketch a triangle passing 3 points, then a line passing to 2 points looks like this way. line passing these two might be just a straight line if the line passing the center of it. But these two might also look like this way. But triangle means like this, right? So when you're really measuring those angles, then the sum is going to be less than 180 because in traditional Euclidean triangle looks like this way, right? A little bit larger than that. Okay? So these are two models, right? Nice models for each of these. So remember that, right? By the definition of Euclidean geometry and non-Euclidean geometry, and what is the kind of nice representative of that. And this one is for getting the case, so let me just skip it. And this is how to sketch the orthogonal circles. So please follow these steps, okay? And try to get uh, that wheel, the circle in the Poincare disk, okay? So after you have this orthogonal circle each other, then this will be the line, the model for the line in the hyperbolic geometry. Okay, so please do this one and let me know if you have any question about it. Okay, so after you do that, you can sketch the triangle or line segment in here. Okay.